Good morning. Today we're going to talk about section 8.4, testing claims about mu. In other words, testing claims about population means. You may recall population, the symbol for population mean is mu, and we're going to test claims about mu in this section with sigma known. Now this should sound somewhat familiar, as in chapter 7. For this section, we're making the assumption that the population standard deviation is known. Alright, let's take a look back. You may recall in our last online class in section 8.3 we tested claims about a population proportion, little p, right? And to do that, let's see, we've got a big population here, possibly millions of elements in this population. The population proportion with some desired characteristic typically is never known for sure. What we did was take a sample proportion, p hat. Remember, that's a raw number of items with a desired characteristic, of course divided by the sample size, and we tested claims about p. Somebody says that p equals something, and somebody says alternatively that p may be less than or greater than or not equal to that same something. So what we did is used p hat, our sample proportion, to compute a z-score. Now we let the calculator do that internally, and in turn the z-score gave us a p-value, and we're going to use the p-value approach in all these hypothesis tests, and we're going to let our p-value decide whether to embrace or fail to embrace, or reject or fail to reject H0. Okay, and to decide that in all these hypothesis tests, we use this indicator. Small p-values suggest H0 is false. Now remember, your p-value is based on sample data. Your p hat determines a z-score, and your z-score determines a p-value. Alright, so it is totally possible that your sample data may be fluky. Hopefully not. With a large enough sample, we can be reasonably confident to either reject or fail to reject H0 based on these guidelines. Alright, so that reviews section 8.3. In 8.4, we're going to be doing something rather similar. We're going to be testing claims not about p, but about mu, population mean. And again, in a large population with perhaps millions of measurements, there will be a population mean value, which typically we never know. And someone may make a claim about mu. Someone claims that mu equals something, and so the alternative claim is then that mu is greater than that same something, or less than, or not equal to that something. So just like we used p hat to test claims about p, we will similarly grab a sample, compute a sample mean. We will use our sample mean to compute a z-score, and the calculator, of course, does this upstream according to the z-score formula. Z equals x bar minus mu over sigma over the square root of n, formula for z-score that will hopefully look familiar to you. And your z-score will then determine a p-value. And much like in section 8.3, our p-value will be the indicator of whether to reject or fail to reject H0. Alright, so we're basing our conclusion really on a z-score, and I want to give you an idea what's happening here upstream in your calculator. Since we're going to be converting our sample mean to z-scores, well, what happens is your test data will come out with a z-score, or can be converted upstream with the calculator into a z-score, which I'll indicate here on the graph like so. All right, let's say I've got some hypothesis test situation, and I've got some sample data, a sample mean that converts to a z-score that I've marked on this graph. All right, a z-score will determine a tail area, and that tail area is called the p-value. All right, now, as we know, if the p-value is small, well, that means your sample mean data is extreme. All right, I think you can buy this. If this area, if this tail area is, and that is the p-value, it's that tail area. If that tail area is small, that means this score is pushed off into extreme ranges. All right? And if your sample mean data is extreme, that implies that something is wrong with the assumption that H0 is true. So let me write that down. I'll say this suggests that H0 may be false. Okay? So that's why small p-values suggest H0 is false. And of course, conversely, if your p-value is large, well, I can draw kind of a crude graph of that. And remember, we're converting everything to a z-score to compute our p-value. Well, if your p-value is large, that means the tail area determined by the z-score of your sample data is going to be big, relatively big. I mean, that's your p-value. Your p-value is your tail area determined by the z-score of your sample data. All right, if the tail area is large, that means this score, this z-score, is not pushed off into extreme ranges. All right? So let me write that down. Then if your p-value is large, your sample mean is not very extreme, and that's another way of saying your sample data is not statistically significant. Okay, let me write that down. Sample data, or in section 8.4, it's your sample mean, is not significant, not extreme enough to dethrone the assumption that is included in H0. Right? Sample mean not significant enough, write this down, to warrant rejection of H0. Your sample data is weak if you're looking to reject H0. All right. As you might expect, to compute the p-value of sample means, well, much like to compute the p-value of sample proportions, we're going to use yet another command or operator on the TI-83 or 84 calculator. All right, what I'd like you to do is get your calculator out and play along. Let's take a look at this new operator. Well, it's in the Stat menu, not surprisingly under the Test submenu, and number one on that list is z-tests. And it's no accident that that's the number one on this list. This is by far the most used of the hypothesis tests, the z-test. All right, you could probably figure out what's going on here by looking at this menu. I'll walk you through it. Mu sub 0, again, that's the TI code. Hang on a minute. Mu sub 0 is the TI code for your null hypothesis statement. much like it was in section 8.3. Sigma. Now again, we are assuming sigma, the population SD, is known in 8.4 section. X bar, of course, is your sample mean. N is going to be your sample size. And you've got to pick the type of test that you're invoking on mu. You've got a left tail test, a two-tail test, or a left tail test, or a right tail test. And again, the sign in H1 will tell you the type of test. And sometimes that's not so easy to determine from the words of a problem, as we'll see. We'll do all three types today. Alright, once you enter in all this data, of course, just like with the one prop z-test command that we used in section 8.3, you highlight and select calculate. And the results screen will look something like this. Basically, it reminds you what test you're using. You'll have a mu is greater than statement. That's really the TI code for the alternative hypothesis, or H1. The calculator will return the z-score of the sample mean. And this statement P equals, and this is going to be your p-value. This is really what it's all about here. This is what I'm going to be looking for, that third or really fourth line of code in that results screen. Alright, the calculator will also remind you of the sample mean and the sample size that you plugged in the input mode of your calculator. Okay? Alright, so the framework is the same. The operator on the calculator is very similar to the operator we used in section 8.3. So let's just jump in and do an example. I want to do one of each type here. I want to look at number 7 on page 430. I believe this is your homework list. Let me read the problem to you. You might want to get it out in your books. Writing a hit song. In the manual, how to have a number 1 the easy way. It is stated that a song must be no longer than 3 minutes and 30 seconds or 210 seconds. A simple random sample of 40 current song hits results in a mean length of 252.5 seconds. Assume the standard deviation, they really mean population standard deviation, that's kind of implied there. Assume that the population standard deviation of song lengths is 54.5. Use a 0.05 significance level to test the claim. You hear the bells go off? Test the claim. What claim? That the sample is from a population of songs with a mean greater than 210. With a mean greater than 210. Alright, so we're going to test that claim, and clearly that's going to be our alternative hypothesis. Remember, H1, the alternative, is always an inequality statement, either greater than, or less than, or not equal to, right? So this is going to be a right tail test in this exercise number 7. Alright, the null hypothesis is not stated, but we know by implication the null hypothesis is always an equality, the equivalent equality to the statement mu is greater than 210. Alright, so step 1 is done. We're going to have the same 3 steps that we had in the previous section. Step 1, state hypotheses. Okay? Number 2, we want to compute the p-value. And again, your p-value is determined by your sample data, which will be computed for us by the calculator. Alright, well, let me write down some given information here. Remember, in this in this problem we took a sample of 40 songs. The sample mean length of these songs was 252.5 seconds. The population SD was assumed to be known at 54.5 seconds, and the level of significance was 0.05. Alright, I don't want you to lose sight of what's going on here. It's possible to work these problems out kind of mechanically and not really appreciate what's going on. So let me stress this. Someone is challenging this implied assumption that mu equals 210. And they're challenging that statement with this sample data. Now, clearly 252.5 seconds is greater than 210 seconds. The idea here is that difference significant or statistically significant enough to deny the claim or reject the claim that mu equals 210. All right, that's what we're doing here. That's what we're putting to the test. All right, let me go back to yellow here. We're going to compute the p-value, and let's see, I'm going to go to stat. Get your calculators out. Go to stat mode and the test submenu, and again, this is a z-test. Remember, your p-value is depending on a z-score here, and we are testing a claim about a population mean, so we'll use z-test. Recall, if you're given summary statistics like we are here, you'll want to pick the stats mode, not the data mode. We'll do the data mode later. Alright, what are we going to enter in here? Mu sub 0, again, that's the TI code for the statement mu equals 210, labels as H0, so the TI labels that mu sub 0. Alright, so we'll put mu sub 0 equals 210. Sigma is 54.5. That's assumed to be known, and notice the TI calculator knows that you're assuming that to use the z-test, so they've labeled it as sigma. That's nice. X bar, the sample mean is 252.5 in seconds. The sample size is 40, and for the type of test we will want to pick greater than mu sub 0, because we are in a right-tailed test here. The sign of H1 always determines what type of test. Alright, of course, we'll now highlight calculate and select, and we get the following result screen. Well, the calculator reminds you of your alternative hypothesis. The calculator returns the z-score of your sample mean. Again, that's computed upstream, and I wish this was a capital P in the calculator. Maybe they don't have that facility on the calculator screen. This is the p-value, 4.07 and change, E minus 7. Now the calculator also reminds you of the sample mean in the results screen in case you forgot, and the sample size. Alright, so this is what we're searching for here. This is the p-value, as you probably know. Alright, so just a minute to talk about scientific notation. This E minus 7 just really means it's 4.07 times 10 to the minus 7th power. And we've dealt with scientific notation many times so far in this course. All that means is you've got a decimal point and a 407 with 6 zeros in between. Basically, you move your data points 7 places to the left. And if I had a p-value this small, I'd probably just call it 0 plus. Alright, so step 2 is done. We computed the p-value. Now you may recall step 3 from section 8.3. Again, the framework is the same. We compare the p-value to the alpha level. Well, my p-value I have determined to be rather near 0. The alpha level, the significance level, really the burden of proof, the height of the hurdle that has to be overcome by your sample data to reject H0. Here it's 0.05. And of course, this p-value is less than 0.05. And remember, small p-values suggest H0 is false. Doesn't prove it, but suggests it. Right? And you might ask, smaller than what? Well, of course, it's smaller than alpha. Alpha is going to be your bar, so to speak, that you've got to overcome. Alright, so I will reject H0. And probably a good idea to put your significance level. Your answer may change depending on your levels of significance. Reject H0 at alpha equals 0.05. And the book sometimes asks for an interpretive statement. Interpret the previous results. Well, let's see, I'll be a little more verbose here. If your p-value is 0 plus, that implies something. That implies there is essentially a 0 probability of getting a sample mean of getting a sample mean of the one that you got, the one that we got from data, essentially a 0 probability of getting a sample mean of 252.5 if the population mean is indeed 210. Okay, so the implication here is there is something maybe wrong with this assumption. There's something maybe wrong or false about that statement that the population mean is indeed 210. Alright, so data, your sample data is strong or significant in justifying a rejection of H0. Okay? So again, I suppose your final answer would be this statement here, rejecting H0. Remember, your answer in a hypothesis test is always either to reject or fail to reject H0. Okay? Alright, so that's a right-tailed z-test. And let's check out another one. I want to look at number 8 now. On page 430. And please take a minute to familiarize yourself with that problem. I'm going to read it to you now. Red blood cell count. A simple random sample of 50 adults is obtained. I'm going to start writing some of this stuff down right now. And each person's red blood cell count is measured. The sample mean is 5.23. Alright, so they got some sort of, what is it, cells per deciliter or something? Or cells per microliter, sorry. Alright, the sample mean from these 50 people is 5.23. The population standard deviation for red blood cell counts is 0.54. So again, we're assuming, excuse me, we're assuming that sigma is known here. Use a 0.01 significance level to test the claim. All right, the bell should go off. Test the claim that the sample is from a population with a mean less than 5.4. Population mean less than 5.4. Okay? Which is a value often used for the upper limit of the range of normal values. What do the results suggest? All right, so this is the claim I want to test, and of course that's going to be H1. Right? H1 is always greater than, less than, or equal to, and H1 determines what type of test. Again, by implication, the null claim, the null hypothesis is that mu is 5.4, the corresponding equality. And step 1 is done. I've stated the hypotheses. Excuse me. Alright, let's go on to step 2 now. Compute the p-value. And again, let's not lose sight of what's happening here. Again, let me highlight that before we go on to computing the p-value. What's really happening is the assumption is that this is true, and we're challenging that claim with this sample data. Now clearly 5.23 is less than 5.4. The idea here is it's significantly less than 5.4, significant enough to warrant rejecting the null assumption. Alright, so p-value, of course I'll go to stat, tests, and choose z-test. Now for your input mode, of course we are given summary statistics here, so don't go to data mode, go to the stats mode. Highlight and select stats. The calculator will prompt you for mu sub 0. Again, that is TI code for the null hypothesis. So H0 is the claim that mu equals 5.4. So I'll put 5.4 on that line. The population standard deviation is assumed known to be 0.54. The sample mean is 5.23. Hang on. The sample size is 50. And for the type of test, of course, this is going to be a left tail test. So highlight and select less than mu sub 0. And of course, we'll highlight and select calculate. See, and I get a p-value of 0.013. So from the results screen, we'll get a p-value of 0.013. Okay? Alright, so step 2 is done. Now it's easy. Now we compare the p-value to your alpha level. The p-value we computed is 0.013. The alpha level, let's see, did I write that down? Yes, it says use 0.01 significance level. Alright, so the p-value here is greater than alpha, larger than alpha, and again, large p-values suggest H0 is true. There's nothing wrong with that assumption. Or at least that the data isn't significant enough, not extreme enough, to warrant rejecting H0. So in this problem, in this hypothesis test, I failed to reject H sub 0 at, at alpha equals 0.01. Right. So this is my final answer for this hypothesis test. And if I was to interpret this statement, and say the sample mean is not extreme enough, not significant enough to warrant rejection of H sub 0. Alright, so we've done a, let's get a new screen here. We've done a right-tailed z-test. We've done a left-tailed z-test And now I want to do a two-tailed z-test. And to that end, we're going to call up number 19, number 19 on page 431 in your textbooks. Alright, now please turn there and familiarize yourself with the problem. Of course, I'll read it here. Number 19, FICO credit scores. If you don't know what a FICO credit score is, you'll know that soon enough. A simple random sample of FICO credit rating scores is obtained and the scores are listed below. As of this writing, the mean FICO score was reported to be 678. By implication, they're referring to the population mean is reported to be 678. Assuming the standard deviation of all FICO scores, again they're implying it's a population SD, is known to be 58.3, use a 0.05 significance level to test the claim that these sample FICO scores come from a population with a mean equal to 678. Test the claim that the mean is 678. Alright, so this is going to be my null hypothesis, and by implication the alternative then is going to be not equal to 678, or that the mu is not equal to 678. That's by implication. If they state H0 as an equality, H1 will then be a not equal to statement. Alright, so step 1 is done. We've stated the hypotheses, but notice they don't give us a statistical summary. They don't give us a sample mean. They don't give us a sample standard deviation. All they do is give us raw data. Well, we'll compute our p-value of the sample mean by entering in raw data on the calculator. Okay? So step 1, let me relabel this. Step 1 is done. Step 2, compute. We still want to compute the p-value of our sample data. Alright, so what we'll do is enter our raw data into our calculator like we've done before. Write this down. If we're given raw data, you might want to use the data input mode on your calculator. Well, let's see. I want to enter this raw data in to my calculator. You'll recall how to do that. You hit Stat and then Edit, and essentially we will clear L1 and enter in the raw data that you're given in problem 19. So that may take a minute to do, so go ahead and do that. I've already done it, so I'll go on. Once that new data is entered into list L1, I'm now ready to test. I go to that hypothesis test mode, hit Stat, Test, of course Z-test. Now for the input mode, of course, we're not going to pick data. We're not going to pick stats here. We're going to pick data because we're doing this with raw data. Okay? So enter the new data into L1 and pick data for your input mode. The calculator then prompts you for the null hypothesis. Well, that's mu equals 678. It also prompts you for the population SD, which was given as 58.3. Alright, now the calculator, since you're in this data input mode, it prompts you where to find the data. Well, of course, we entered it into list L1. Alright, frequency, that just means the frequency of all data here. I would just leave this at the default 1. And of course, we're in a two-tailed test here. Alright, so highlight and select not equal to mu sub 0, representing a two-tailed test. And again, in the results screen, the calculator reminds you of your alternative hypothesis. It returns a z-score of your sample mean. And again, we are interested in the p-value here. Again, that's 8.37 times 10 to the minus 7th power. And just like in our first example today, I'm going to call that 0 plus. The calculator also returns your sample mean and your sample standard deviation, which I won't pay much attention to right now. I'm just going to write down my p-value. Next to my alpha level, they said to use an alpha of 0.05 to judge whether this data was significant. This is step 3, compare and conclude. Of course, my p-value is less than alpha here, and small p-values suggest H0 is false. How small? You might say smaller than alpha. So if your p-value is smaller than alpha, we reject H0. And probably a good idea to put your significance level in your final answer, because that might change your answer depending on the significance level chosen. Reject H0 at alpha equals 0.05. In other words, if we put an interpretive statement here, the sample mean is significant, statistically significant enough to warrant rejection of the null claim that the mean is 678. Alright, we're approaching the 37-minute point. We've done z-tests, right tail, left tail, then two tails, and introduced a new operator on our calculator. So that's enough for today. We'll call it a day. Thank you.